So for the last couple lectures, we've been talking about different classification methods. And we've been talking about linear classification methods. I guess the first method we did was k nearest neighbors, and KNN is not a linear classifier. But then we have been talking more recently about linear classifiers. And the preeminent example we had looked at was Lda. And today we're going to talk about another classifier called logistic regression. So Lda, just to do the quick recap here, we had our discriminant functions, which were approximating our probability that y is in our class given our data. And we had approximated this probability by using Bayes' rules, first to flip this around, so we can calculate it as the probability of observing our data point given our class label of the data point times the probability of observing that class label. And this was just using Bayes' rules, and this is just proportional to, because if we really wanted to make it equal to, we'd have to divide through by the probability of observing our data. But we don't particularly care about that, since it doesn't depend on the class, at least for now. And so we had said, well, this is just proportional to our class conditional probability of observing x times the probability of being in that class. And of course, we had modeled this first part as normally distributed with a mean mu that depends on the class, so we'd call it mu c, and a variance sigma squared that was shared among the classes. And we had just modeled this as some kind of arbitrary discrete distribution here. And so we're just going to call it pi c. And you could relax the assumption of the equal variances. That would give you what's called QDA. But today we want to talk about another method, which is called logistic regression. And the reason I went back over that recap is Lda is uses Bayes' rule to calculate this probability. And logistic regression, what we're going to do is we're going to look at our discriminant function. It's, again, going to be looking at this probability. We're going to model this directly. So logistic regression is going to model this conditional probability directly. So let's first look at the binary case. So we'll say binary logistic regression. And binary logistic regression, if k is the number of classes, then binary logistic regression, or binary, refers to the fact that we have two classes here. So here, our y can either be 0 or our y can be 1. It can take on one of two values. And our discriminant functions, we'll have two of them, right? So if I generically say my discriminant function for class 0, delta 0, and my discriminant function for class 1 is delta 1, right? Delta 0 is going to be the probability that I observe that y being 0 given whatever x I've got in hand. And similarly, delta 1 is the probability I have my y is in class 1 given the data I've observed. And of course, these are 1 minus each other, right? Because probability y is 0 given x is 1 minus the probability y is 1 given x. And the probability y is 1 is obviously 1 minus the probability y is 0. This, another way of saying this is that the sum of these things has to be 1, because they have to sum up. That's probability. So this is 1 minus, they're just 1 minus each other. delta 0 is 1 minus delta 1, and delta 1 is 1 minus delta 0. And so in the binary case, we actually only need one of these. Discriminant function, because we can always get the other. Can always get the other. All right. I only really need to talk about one of them. Another way of thinking about this is that, for example, let's call, and we'll make some kind of arbitrary choice. Let's call p of x to be class 1 discriminant function, which is the probability that I'm in class 1 given my data. So that's supposed to be probability y is equal to 1 given, let's do big up a bar, given my data. Right, so p here, or p of x, is my is the probability that I'm in class 1. And our rule, we said we're going to model this directly, so we'll talk about that. After we model it directly, our rule is that we'll classify as class 1 if this p for our given x is bigger than 1/2. And the reasoning being that we can basically say that since if p of x, which is delta 1 of x, is bigger than 1/2, since delta 1 and delta 2 of x sum to 1, then delta 0, sorry, not delta 2, delta 0 sum to 1, then delta 0 of x has to be less than 1/2. So if delta 1 is bigger than 1/2, because they sum to 1, delta 0 has to be less than 1/2. And so my discriminant function for class 1 has to be bigger than my discriminant function for class 0. Hence, I predict class 1. And this is really an if and only if. We can make these if and only ifs, right? So if I think it's class 1, I predict class 1 if my probability is bigger than 1/2, and if it's less than 1/2, I predict class 0, right? Now you could do this for any binary classifier. This isn't anything special. Let me back up on that statement. You could do this for any classifier where the discriminant functions need to sum to 1, and you work with binary classification. If your discriminant functions don't sum to 1, obviously you can't assume they sum to 1. So, but the rule is basically, so we don't even need to ever reference delta 0. We can just say our rule, here's p of x, which is delta 1, and our rule is just, if it's bigger than 1/2, we classify as class 1. If it's less than 1/2, we classify as class 0. Okay. So, given I've observed some data, maybe some little x, notice that y is 0 or y is 1. We have a name for that type of random variable. We call y, let's say, given my data, a Bernoulli random variable, right? So Bernoulli random variables take on either 0 or 1. So all this is a Bernoulli random variable. And so we could write our setup simply as y given x distributed Bernoulli, and then the parameter of Bernoulli is the probability that I observe a 1. Well, what's the probability I observe a 1? We call that p of x. So that's real nice, right? So that harkens back to Bernoulli random variables, and that's all our setup is. And the game now is, how do we model P of X? So let me say this. The game here, basically at this point, is how do we model this P of X? And, okay. So how can we model this? We have, up to this point, I'm just generically describing basically binary classification, where we have this one little assumption that we're going to correctly model this probability, and so my discriminant function is going to add to 1. I haven't even said that the discriminant functions are positive. So one way I could do it is just say, okay, P of X is some linear function of my covariates, something like that. And let me even write this simpler. Let's just call it beta hat transpose of X. Maybe X includes an intercept term. It doesn't really matter. And I could learn my beta hats from regression. And we talked about this a little bit at the end of last lecture. One of the problems that we can get is what we call masking. And so let me draw 2 pictures here for you. If I have, say, a bunch of classes, we're gonna move out of the binary world for a second here. If I have a bunch of classes, because this problem tends to manifest in when you have multiple classes, what happens when I do this kind of regression thing, which I talked about last time, is, maybe that's my delta 1, maybe that's my delta, I guess that's class 3, and then the classic picture is, what if my delta 2 looks like that? I would never predict class circle, because delta 2 is never the largest. It's masked by delta 1 and delta 3. And the reason it gets masked is because because of the rigidity of this linear assumption here, where and the way it learns these discriminant functions is not going to be kind of amenable. You're going to run into this problem quite a lot. And so one thing you can notice that's a bit weird, for example, if we go back to our binary world, is that if I wanted to learn, say, if I just had red x's and green squares, I could learn my green square, the way I would learn this, discriminant function. I guess this would be the, this is a different problem, right? So basically what happened is I'd put zeros for my red x's. I guess you could have your green circles in there too. This is going to give me what I want. And I could learn my discriminant function here. And you would basically, so this is the setup. We'd have zeros for all the classes, but the class we want to learn the discriminant function of. We'd put our red square, or our green squares at 1, and then we'd learn this regression line. And that would be delta 3. And in some sense, you could do this. So if we go back up to our setup here, we're supposed to be modeling P of X, which is a probability. And so this is weird, a little bit weird to do, because if we notice up here, P of X is bigger than 1 here, and P of X is less than 0 here. And so this is a weird model of P of X, because it can predict P is bigger than 1 and less than 0. they could still, by discriminant function could still sum to 1. We could put that constraint here. It doesn't mean they have to be all positive, so you could have negatives that cancel out with things larger than 1. So you can get some kind of weird modeling down here, and it gives you this intuition that this is not a great way to model probability because this linear function is kind of unbounded. And this is probably not a great idea. Oh, has anyone called me out on this? These lines are backwards. This should be the green one, right? Surely the green one should be higher. I always do this. So the green should be higher near the greens, and the red would be higher near the reds. Sorry, those are backwards. Now those green lines match up, right? Okay, that makes a lot more sense. But point holds. It's a weird way of modeling its probability, and the reason you get masking is because these things can kind of grow unbounded. They're not bounded between 0 and 1. And this kind of generic problem we're setting up, we're supposedly modeling this probability, and it's a bit of a weird way to model that probability, and it can lead, because it's linear everywhere, it doesn't, it's not bounded between 0 and 1, it can lead to these masking problems here. Where what we'd really like to happen is, let me just draw one more picture. A better way of doing this is, let's say, and I get my blue circles here and my green squares here, right? It would be its high, let's say that's all backwards. That's 1, that's 0. It would be its high over where it's green, but then it drops down real fast over here. It's high where it's red, but it drops down fast there. And then it's kind of high where it's blue, but it drops down where it's not, right? And so this is we got this from something like LDA. We didn't have these masking problems because LDA is developed from a probabilistic viewpoint, and therefore it doesn't run into these kind of silly masking issues. So probability is cool, right? It helps us in this situation do things that a little bit better, that are more generalizable. Now, if you have a few classes or low dimensional space, probably doesn't really matter, but if you have a bunch of classes, this is going to be very important. What you could do is you could try and learn these things empirically. You wouldn't have to actually do probability. You could actually just try and learn more complicated functions. Instead of doing lines, you could do something quadratic or something. I mean, that's basically some kind of what we'd call a non-parametric way of doing this. And eventually it's kind of going to effectively approximate these kind of more complicated shapes here. That's an aside. So that's called as way 1. I guess this is a better way. Let's just call it way 2, which is logistic regression. And that kind of picture I just drew up here is basically what logistic regression is going to do. So and we're going to talk again about the binary case for now. So let's go back to the binary case. But here, if I have my red x's here, and I just have in some other class where I have my training data looks like green squares there, you could imagine fitting my delta green, to be some kind of what we call sigmoidal function that is close to 0 over here, close to 1 over here. And so this is delta, let's say, square, and these are so-called sigmoidal function because it's kind of S-shaped. And then my corresponding red would look something like, that. Close to 1 over the red class, close to 0 over the other class, right? So logistic regression basically proposes we do this directly. So logistic regression says let P of X, that I'm modeling, be an S-shaped curve like this. And the particular S-shaped curve is a logistic curve. And it's going to be logistic of, so I'll write this out, of beta naught plus beta X. So I'll write it like that. Or more generically, we could write it just as beta transpose X. my x vector is whatever transformations of variables. It could include a 1, in which case you've got to get an intercept term here. So the aside here is that the logistic function is basically a sigmoidal shape. Logistic of x is 1 over 1 plus e to the negative x. And what that looks like is, if I draw my stuff here, here is 0, here is my 1, and here is 0 on the x-axis. My logistic function is going to pass through 1/2 there, and it's going to look something like this. So it's an S-shaped curve. This is logistic of x. Now, we don't necessarily want it centered around 0. We don't want this point, this kind of halfway point, to be at 0. And so we can look at linear transformations. We can do additive shifts. We're not just going to look at logistic of x, because that would force the center to be at 0. But you can do all other kind of linear transformations, which can shift this thing around or stretch it in various ways, right? So, like if I do something like, let me just draw 2 things. If I have like logistic of x minus a, that will just put this center at a. It will still start at 0 and go up to 1, but if I draw it correctly, the point where it crosses 1/2 here will be pushed over to a, and you could do other things. You could scale it, right? So you could do logistic of x over a, which presumably is going to scale it by a. So it would, I guess if my 0 point were there, it would stretch it out. So it would make it smoother instead of going really sharp. I guess, one way to think about it is you could either make it really sharp. It's supposed to go through 1/2, right? You can make it really sharply do that, or you could make it really slowly do it. I'm not very good at drawing pictures here, you can tell. But you can mess with how all these things, you can combine all these things, and that is basically what we do here by allowing us to have not just a logistic of x, but logistic of beta x, and you can kind of move it around, stretch it, and squish it. And so it allows you to very flexibly model over the x space here, right? So that's the logistic function. The logistic function has an inverse called the logit function, which is log. You could just solve it, log. So maybe, let's say logit of y is log of y over 1 minus y. And this is basically logistic inverse of y in this case, right? So it's the inverse function. It's called logit. But the logistic function is just a S-shaped curve. There are actually other ways of doing this. You can work with something called a probit function, which is a similar S-shaped thing. That's called probit regression or something like that. But there's kind of theoretical reasons why people like logistic, and frankly, it's probably good enough. We don't need to do anything too fancy. Okay, so let's just recount what our model is. Logistic regression in the binary case. And it is that the class label y we observe given our data comes from a Bernoulli distribution, where the probability depends on what x we observed, and p of x is modeled as basically 1 over 1 plus e to the negative x, negative beta transpose x, or equivalently logistic of beta transpose x. And it's just an S-shaped curve. And so we're directly modeling this thing. Okay, so that's the model. That's a very statsy model. We'll talk about some of the other models we talked about. This is, of course, a statistical learning course. And so the question becomes, how do we learn beta hat. How do we get an estimate? Because basically we need to, we're going to need to estimate beta hat, and then we have our predictor. We have our discriminant functions, and we can plug in the estimate beta hat, and we can start making predictions. According to a rule, which is that if this predicted probability is bigger than half, we're going to say it's class 1. If it's less than half, we'll say it's class 0. And the way we do this is with what's called maximum likelihood. Maximum likelihood estimation. So if anyone has taken 452, this is something you've definitely come across. I guess that's not a formal requirement for this, so but it's actually a pretty straightforward concept. So the idea is that what we're going to assume is that for our training data, our y-ends, given the corresponding x-ends, are independently distributed following this principle, follows of Bernoulli, and x is modeled as this logistic function p of x. And you could even write this little subscript beta here to remind us that this thing depends on beta, right? Which is an unknown parameter. So p beta of x is logistic of beta transpose x, right? And what we're going to do is let's get the joint density or probability of y-ends conditional on the x-ends. So basically what we want to find is the probability of observing, I'll use notation here, y1, y2, y3, all the way up to yn, given x1, x2, x3, all the way up to xn. Now this probability, because it depends on this p, which depends on beta, is a function of beta. So we could think of this thing as a function of beta. Let's call it L, and it's whatever you call it, it's a function of beta. Typically in stats, we call this L for likelihood, and it is the so-called likelihood function of beta. The idea being that for different values of beta, I will get different probabilities here. And what I want to do, I want to find the probability of beta, or find the value of beta that has the highest probability of having occurred. So the way you can think about this likelihood function is that for different values of beta, it's going to tell me the probability I observed my y's given my x's. So if there's a value of beta where that's high, that's probably correct. If the probability that beta, is negative 100, given given this calculation, so I have my y's and my x's, and I can say, okay, if beta were negative 100, what's the probability I observe this data? If that's really small, probably beta is not negative 100. If it's high, when beta is 1, the probability of beta 1, I said, this is likely, this is probable under my model here. You would say, okay, that's a better estimate of my beta. We're just going to choose the one that is the, quote, most likely. So this is what we call the maximum likelihood estimation. And so you're maximizing this likelihood. You can view it as a minimization problem too. You could throw in a negative, and you could view it as minimizing a certain loss function, and indeed it pretty much is. But in this case, just throw in another wrinkle here. We'll think about it as this is very much the traditional way logistic regression is taught, because it was developed in the, say, 50s, when people are thinking a lot about these probabilistic models, whereas some of the new machine learning stuff, say neural net, which simple neural networks are just logistic regression. So, by the way, aside, after this lecture, you can say, I understand simple neural networks, because very kind of simple neural networks are just logistic regression. We'll get to that hopefully later in the course, but this is developed in kind of the 50s, and talking about probability, and so this is very much a traditional way of presenting it. You could present it in other ways, and people will, but being a statistician, I'm going to present it this way. Okay. The point is that all of these we have made this model, we're assuming that the conditional distributions of these y's given the x's are independent. And so we can actually just break up this thing into a giant product of probability of observing yn given the x events. Because all of them are independent, that's what independence gives us. And indeed, we actually can go a couple steps further. We know what this probability is, right? So our aside here is for Bernoulli. What's our PDF? Let's call it f of x, whatever. If x is Bernoulli with p, our PDF is what? One way you can write it is p to the x times 1 minus p to the 1 minus x. That's the slick way of writing it. Notice when x is 0, you get 1 minus p, and when x is 1, you get p, so it's equivalent to the more traditional way of saying that the PDF is p for x is 1 and 1 minus p when x is 0. In any case, our p here now for this model is not p but p of x, and it depends on beta. So let's just say, so replace our p's with its p depends on beta x, and our x here is actually, maybe I should write this in terms of y, right? Really, we have y is distributed Bernoulli, so that would take that place, right? So if I say y is distributed Bernoulli, that would be a PDF. And then by 1 minus p depends on beta of x to the 1 minus y, right? And what do we want to do at this point? But let's just take a couple more steps further. We know what PB of x is. It's P beta of x is, right? It's a logistic function. So this thing is 1 over 1 plus e to the beta transpose x to the y. And then this is 1 minus this. So we can even write it as 1 minus 1 over 1 plus e to the... Did I write this logistic function correctly? There should be a negative in here. I always do that. Don't forget your negatives. Negative, negatives, negative, negatives. The logistic function itself has a negative, so that goes there. Okay. And then this is to the 1 minus y. Of course, it's y sub n in our product here. And so typically people will, instead of working with this product likelihood, they will work with the log of it. It doesn't really even matter. The point being is that, so this is our likelihood function. You can see now, we're not going to derive the whole thing, but you can see that this thing is a function of beta, depends on our x sub n's, depends on our y sub n's, and the maximum likelihood estimate here is, we're going to say beta hat is the maximizing argument of this likelihood function. So all that is to say, that's fancy notation, just to say we're going to choose beta hat as the value of beta that maximizes this likelihood function. Cool. And how do we do that? Well, unfortunately, unlike problems in, say, 452, this is not analytically doable by hand. So this runs into the realm of optimization, and I don't know anything about optimization. Ask Dr. Kincaid, ask Dr. Nin. But really, it becomes an optimization problem. And so let's say not intractable, but no analytical solution. Give to friends in OR, which I guess is many of you, right? So you give it to an OR person who knows how to optimize something, or you plug it in an optimizer. Turns out So this is as far as I can go. There are some fun things you can do here, so I'll just point things out. We're not going to derive all this. So it turns out you can solve this the classic way of solving this, which again was developed in, I don't know, the 50s or something, back when no one had computing power. The classic way to solve this was with gradient descent, which many of you may be familiar with, because so basically all you do is you calculate the derivative and you try to find where that derivative is zero. If you kind of follow the derivative points in the direction you want to go, or opposite direction. I guess in maximizing it would point in the right direction. And you follow the derivative until you find where it's about zero, or you follow the gradient, because this beta could be a vector. And so it turns out that we can cast gradient descent in this problem as, so a gradient descent is an iterative procedure. I mean, this is not an optimization class. So I don't want to get too far into it, but it's basically an iterative procedure where you take a step in the right direction, you calculate a gradient, you take another step, you calculate your gradient. The gradient tells you where to go. You just kind of follow your nose. Let me just draw the picture here. For many of you, this is obvious, but right. So if you have this function that looks like this, right? If I calculate my gradient at this point, my gradient would be negative. It would tell me take a step in this direction. It would tell me take a step in this direction, right? If this is gradient minimization, I guess I can draw for maximization, right? Here's the function I want to maximize. I want to get to this point. So if I'm here, I calculate my gradient. It tells me it's positive. It tells me it's positive. I take a step here. I take a step here. So you just kind of successively take little steps until eventually you get to my optimum point there. So this is how this problem is actually solved with gradient descent. However, there's kind of a more interesting statistical way. So an OR person would opposite and solve with gradient descent. There's a more kind of interesting statistical way of looking at this, which is you can cast gradient descent, which is this iterative procedure, as a series of weighted, and maybe we'll talk about weighted things later, of weighted least regression, let's say. So it turns out the update step, so at each point you can calculate this gradient, take a step, calculate the gradient, take a step. In this iterative procedure, you can cast that as a series of solving weighted regression. And so this is called, you will see this occasionally if you read about logistic regression. It's just called IRLS, which stands for iteratively reweighted least squares. So basically, it's an iterative regression process. So you can connect it back to a regression or a weighted regression kind of problem, which is fun. And statisticians like that a lot. This allows us to study the behavior of it in cool ways. But ultimately, the point is you form this likelihood function here, which involves your x's, your y's, your betas. It doesn't have a solution that you can write down. So unlike just normal regression, you can just write down a solution. There isn't one. You got to solve this maximization problem to find the most likely estimator beta hat, and you have to solve it with an iterative procedure, which is slower than some other procedures. Now, in modern day, it's not that slow compared to anyone's 5-year-old cell phone can solve these problems, but it is algorithmically much slower than something like regression or even something like LDA, because those have closed form solutions that you can just calculate analytically. And this you actually have to solve an optimization, and that can cause pain sometimes. You'll see that occasionally when you run the code, it will hiccup and not work as well as you'd like. Okay, so let's talk about the multi-class problem. So this is binary logistic regression, and this is, I think, the kind of extent to which we're going to go into it. It's a really, really, really nice method because it has some of the nice things like regression, where you get this beta vector that you can interpret, but you don't but it's a classification technique. So there's reasons why it's called logistic regression. It lives in a family of what's called generalized linear models. So a regression is a linear model. Logistic regression is a generalized linear model. And so it has many of the same flavors as kind of regression, hence the name, but it's for classification. You have betas, you can interpret betas. They're a little more complicated to interpret. You can get p-values, you can do all this same kind of stuff. So in this statistical learning class, as the point is not as much as is more on prediction than on kind of interpretation of a model. We're not going to talk about that as much, but a traditional, class, I know here in undergrad at like 352, 353, we teach, Dr. Sasanoska teaches this very well. There's a wide and vast literature on logistic regression because for, 30 years, it was just the dominant classification technique. And to be fair today, it is super useful, especially if you want to interpret your results. So don't always, don't get too fascinated with the shiny objects of modern fancy machine learning techniques. Sometimes you want to know what the hell your classifier is doing, and you need to be able to interpret, or do causal inference on a model. And so you need something simpler that you can actually understand, like logistic regression. Okay. And often it's just a great method. So we talked about the binary case. Let's talk about the multi-class case. And multi-class case is really just when the number of classes is bigger than 2. I'm going to go into kind of sparing details here about the multi-class case, but we can view it kind of in a similar way. There's many ways to view logistic regression. One way you can view it is that I'm going to model my y-ends given my x-ends, again, as being independent. But instead of having a Bernoulli distribution, which can take on 1, 0, or 1, we are going to model it as what's called a multinomial distribution. And the multinomial distribution is a generalization of binomial. Binomial. Where I have some k discrete outcomes. Where I can get one of these k discrete outcomes. So this is a multinomial distribution. The multinomial distribution is parameterized by, let's say k minus 1 probability. So instead of having just p of x, we'll have a p1 of x, a p2 of x, all the way up to a pk minus 1 of x. So why don't we need all k? They sum to 1. Sum to 1. So only need k minus 1. Just like in a Bernoulli distribution, we didn't need a p1, a p0, and a p1. They sum to 1. We didn't, we only need to think about one of them. In the multinomial case, they sum to 1. So if you know k minus 1 of them, you know the last one because it has to be the last piece that makes the sum 1. So you only ever need to actually think about k minus 1 of them. And you have what's so-called a, quote, base case, just like kind of in regression, where and it's typically the last class is what we leave out. But you only need to ever pay attention to k minus 1 discriminant functions, etc., because the last one's always determined by the others. And so what we do is for these k minus 1 classes, if we let little k be my class, then the discriminant function for little k, another way of viewing this is instead of having it, it's going to be a multinomial distribution, and the discriminant function for little k, which we call, over here, we call the pk's, is probability that my class is k given my data. And we model that. There's a couple ways to write it. You could call it a multivariate logistic. and it depends on k, but it also, and it's not gonna write it all out, but there's ways you can view this as a generalization of a logistic function. It's called multinomial logistic. Often multinomial logistic regression. So when people say logistic regression, they typically refer to just the case where k is 2. For multinomial, they're talking about multiple classes. And it is pretty straightforwardly a generalization. It is e to the beta not for my class k. Let's not even do a beta not. Beta for my class k transpose x sub n, or transpose, I guess in this case it's x, divided through by 1 plus, and the other, and before it was e to the negative something, right? This is 1 plus, we sum over all k classes. So we get a beta for each of our classes. So let me write that out. Beta for each class. So we get some kind of beta for each class. So it's a much more complicated model, because now instead of just beta, we have a whole bunch of betas. Beta 1, beta 2, all the way up to beta k. Notice, even though we don't need k, discriminant function, you don't need k minus 1, there are k betas, because there's no constraint on the betas. And that's why our sum here in the basement is also overall k. That's not a mistake. There are coefficient beta associated with each of them. And I'm just going to say we estimate these with, or we estimate these as MLEs. So it's a complicated maximum likelihood problem, because now we have, beta 1 hat, beta 2 hat, beta 1 hat, beta 2 hat, beta 3 hat, all the way up to beta k hat, which is betas, all of these betas that maximize this whole big likelihood function, which is a function of all of my betas for each of the k classes. So it's doable. It's most of the intuition comes about from the binary case, but you can generalize it to what's called multinomial logistic regression and do multi-class classification. But typically people talk about it as a binary classifier and just talk about the 2 case, although it's eminently generalizable. And again, you have to solve that optimization problem numerically. You have to throw it in an optimizer, ask your OR friends to solve it for you. There's no closed form solution, unfortunately. So it does take some time to fit, but on modern computers in a small data set, you're not gonna really notice it. Okay. So let's talk about the different classifiers we have at this point. And let's go back to the binary case, where k is equal to 2, right? My discriminant function, delta 1 of x, which we're just calling p of x, is 1 over 1 plus e to the beta transpose x, right? And this is the so-called logistic function. And we said logistic function had an inverse. If we look at so this is, let's say it's logistic of beta transpose x. What if we look at the inverse of the logistic function? We apply that. That's the so-called logit function. And the logit function would say is log of p over 1 minus p. That's what the logit function does. And if you believe me that this is the inverse, then logit of logistic should just give me back beta transpose x, right? You can actually sit through and do that problem. How hard is that to do? Shouldn't be very hard. You want to do it? Let's just look at it. All right, p of x over 1 minus p of x is, whoops, and I always figure out my negative here. There's a negative there. What is it? It's, oh boy. We're going to make some work for ourselves. 1 minus p of x is 1 plus e to the negative beta transpose x minus 1 over, I believe that is correct, and which gives me e to the negative beta transpose x, right? And so I want to invert that, don't I? And so p of x over 1 minus p of x. If you believe this is the inverse, this would give me what? That over that. And then I multiply by, so that's 1 over 1 minus p of x times p of x, which is this bad boy, which is just 1 over 1 plus e to the negative beta transpose x, which is just e to the beta transpose x. And so certainly, if I plug that in my log there, I'm just going to get beta transpose x, right? So this is kind of the workings out here. What does this mean? If you believe that logit, which is the inverse of logistic, so is going to look like logistic on its side. So it will look something like that. I guess this would be my 0 point here, and this would be 1. So it's asymptotes at 0 and 1, but it looks like that. So this thing is monotonic, or we could even say increasing. What does this mean? Is that I have an increasing function of my discriminant function that gives me a linear function. Increasing transformation of my discriminant function is linear. This logit gives me back something that's linear, beta transpose x, which means logistic regression is a linear classifier. So we learned another linear classifier. It doesn't feel like it should be, but it is. If you believe the math, it's a linear classifier. So that begs the question of, we've learned LDA, which is a nice linear classifier, and now we've learned logistic regression, which is another kind of linear classifier. And this begs the question about what is the difference between these. And so we can talk about some differences. Let's just make a little table here. LDA and logistic regression. They are not the same classifier, although often they can perform pretty similarly. So LDA, what does it do? It models we said this at the beginning, the P of x given y and P of y, And the important thing is it uses a normality assumption about x given y. So the first thing is that LDA is making a normality assumption about the class conditional distribution, that given y, x is normally distributed. Logistic regression models y given x directly and no normality assumption about x. And so this generally leads people to say that it is more general because it doesn't make a normality assumption about a class conditional distribution. It actually is agnostic to the distribution of x. It's not really directly modeling the distribution of x. This is maybe the main difference that so maybe we can just summarize it in this point, is that, well, let me there's actually a second point I want to make here. So let's call this one. One is about models. And so the fact that this uses this normality assumption is means that logistic regression is going to be more general because LDA makes this more restrictive assumption. What the normality does is make estimates, let's say, easier to get. Estimating betas is computationally more expensive. So theoretically, LDA, you have to have some assumption of the class conditional distribution that you have this normality assumption. So what does that say about the x's? The x's theoretically should be continuous, right? Because if class conditionally the x's are normal, that's a continuous distribution. It doesn't make sense to have covariates that are categorical. On the other hand, logistic regression makes no assumption about the x's, and therefore you could have, say, binary or categorical x's, just like you can in regression. Now, practically, LDA works pretty well, and it doesn't really violate an assumption. It's actually not that big a deal. And on the other hand, the rigid modeling of this normality assumption makes finding these estimates easier to get for LDA. Now, you can cast LDA as a maximum likelihood estimation problem. You will get, just if you do the MLEs under its assumption of normality, you get the estimates that we said you get. And so and those estimates are easy to get and more efficient if x's are truly normal. So if you actually satisfy that normality assumption, the estimates and the classifier is actually going to be better for LDA. But if you think that really isn't true, you probably would want to go with logistic regression because it's going to give you more efficient estimates, although they're going to be computationally more expensive to get. The rule of thumb is that logistic, if normality assumption is true, LDA is going to be something like 30% more efficient. So you'd have to have, say, 30% more data to get as good of an estimate with logistic regression. On the other hand, if you have categorical covariates, x's also include things that are categorical, you probably don't believe normality assumption. You're probably not losing that much going for logistic regression. It's a little more general, although it's a little more computationally expensive. In practicality, these often perform very similar to each other because they're quite similar. They're linear. At the end of the day, they're both linear classifiers, and you're estimating your coefficients in these linear classifiers. So what I'll just say to close here is both, let's say in the binary case, model this thing as you can write it in some way, a discriminant function, as some beta transpose x. So at the end of the day, they're both linear. They're going to estimate that beta hat, say, in slightly different ways. Sometimes that would be more efficient, for LDA if you really believe some kind of normality assumptions. It's going to be a little more computation expensive for logistic regression, but a little more general. So I would say probably, I don't know which is more popular. People tend to use logistic regression a lot because it does kind of more generally lend itself, and you can kind of interpret the coefficients in nice ways like you would like in a regression model. But they perform probably generally pretty similar. So this is one of the nice things I think we do in this class, which is that we're going to teach you the methods. We're going to talk about what the relative advantages are and how they're connected, right? What you don't want to do is teach a course where you just have a laundry list of methods and you don't really understand how they're connected to each other, because I think that's really an important part of the education. Okay, so that is logistic regression, which is the kind of last classification technique we're going to talk about for a bit. And we're going to pause and go back and talk about some regression going forward for a little bit now. Okay, but I'll stop here.